Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen när vi ska presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Physics. We will keep to our tradition and begin in Swedish and then continue in English. And you are, of course, welcome to ask questions in either language later on. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. Till höger om mig sitter professor Eva Olsson, ordförande för Nobelkommittén i fysik. Och till vänster professor Mats Larsson, ledamot av Nobelkommittén för fysik och expert inom ämnesområdet. My name is Hans Ellegren. I am the Secretary General of the Royal Swedish Academy of Sciences. To my right is Professor Eva Olsson, Chair of the Nobel Committee for Physics. And to my left, Professor Mats Larsson, member of the Nobel Committee for Physics and one of the experts in this field. Årets pris handlar om elektroner i blixtbelysning. This year's prize is about electrons in flashes of light. Kungliga Vetenskapsakademin har beslutat att utdela 2023 års Nobelpris i fysik i lika delar till Pierre Agostini, The Ohio State University, USA, Ferenc Krauss, Max Planck Institute for Quantum Optik, Garching och Ludwig Maximilians universitet München, Tyskland, och Anne Luer, Lunds universitet, Sverige, för experimentella metoder som genererar attosekunder av ljus för studier av elektrondynamik i materia. The Royal Swedish Academy of Sciences has decided to award the 2023 Nobel Prize in Physics in equal shares to Pierre Agostini, The Ohio State University, USA, Ferenc Krauss, Max Planck Institute for Quantum Optik, Garching, and Ludwig Maximilians Universitet München, Germany, and Anne Luer, Lund University, Sweden, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. Professor Olsson will now give us a short summary. Please.
Thank you. So this is about attosecond physics. The ability to generate attosecond pulses of light has opened the door on a tiny, extremely tiny timescale. And it's also opened the door to the world of electrons. Back in 1925, Werner Heisenberg argued that this world cannot be seen. Thanks to attosecond physics, this is now starting to change, and we are starting to explore this world. Let's take 1 second, which is the time of a heartbeat. If we now divide that by 1,000, and we divide it again by 1,000, divide it again by 1,000, divide it again by 1,000, and again by 1,000. Now we are at the time that it takes the atom to move. So then, if we divide it by 1,000 times more, we move into the world of the electrons. And that is the attosecond physics. So, attosecond science allows us to address fundamental questions, such as the time scale of the photoelectric effect, for which Albert Einstein received the Nobel Prize in Physics in 1921. We can also study charge transfer processes in materials and in molecules. What this means that we are able to develop potential important applications for future in areas such as catalysis, electronics, and medicine. This year's prize honors the pioneering experimental work of Pierre Agostini, Ferenc Krauss, and Anne Lullier. They discovered that it is possible to generate these attosecond pulses. They developed methods to measure the duration of the pulses, and they also developed techniques for generation both of pulse trains and of isolated individual pulses to be used for fundamental research, but also future applications.
Thank you, Professor Olsson. Now, Professor Mats Larsson will give a more detailed presentation of the prize. Please, Mats.
Thank you. Yes, this year's Nobel Prize in Physics is about science at the time scale of attoseconds. And what you see here is an attosecond related to 1 second, which is approximately a heartbeat. And the ratio of 1 second to an attosecond is the same as the ratio of the age of the universe expressed in seconds to 1 second. And as Professor Olsson explained, we are now in the world of electrons. And let me remind you, electrons are not only working in gadgets like this. They are working in your full body. Chemical reactions are controlled by electrons, and they move on a time scale of attoseconds. This is the beginning. This was an experiment carried out in Paris-Saclay in 1987 by Nobel laureate Anne Lullier and co-workers. And what they did here was they took a very powerful infrared laser and shine it through a gas jet of neon or argon or xenon. And then they looked at the photons coming out from this interaction with a spectrometer, as you can see here. So this is actually the original drawing of their experiment in the 1980s. So what did they see? Well, they saw a number of, the laser has a base frequency. It's about 1,000 nanometer in wavelength. And they saw overtones of this frequency, a large number of overtones. And the overtones first fell off quite rapidly, and then came a long plateau, and then a cutoff. So the question was, what is generating this plateau, and how can it be exploited? And Anne Lullier in particular worked for a decade with different theoretical and experimental methods to understand what this plateau can be used for and how to explain it. So in order to generate very short pulses, you need all these different overtones. And I will illustrate this now by assuming that we have a number of light. We have light with different frequencies. As you can see here, light with different frequencies. And if we now let these different frequencies interact and interfere, what can happen is that they interfere in such a way that at certain points we create an amplification, whereas at many other points there is destructive interference, nothing happens. And what you get is a pulse train of attosecond pulses. So the trick is really to sum up many different overtones. That gives you the bandwidth. But that's for one atom. Now we are talking about several atoms, and several atoms must work together in phase. Otherwise it won't work. And it's the same with the symphony orchestra. If each member of the orchestra would be playing whatever they want, the audience would just experience noise. But if they play in sync, and of course you have the conductor making them play in sync, then we get music. And it's the same with the atoms. They have to work in sync. And this was figured out by Anne Lullier and others, how to do this. Here is an example of an experiment, attosecond experiment. And this gives you a little bit of an feeling for the length scale of such an experiment. It's not an enormous big experiment. And what you see down here in the corner is laser light, let's say infrared laser light coming in. The laser beam is divided in two parts. One part goes to the left and then into the gas jet, where you produce attosecond pulses. The other part goes into a delay line so that you can shift the time difference between the attosecond pulses and the infrared pulses. And then you combine them on a mirror and send them into your experiment. And out comes electrons that you can observe. And this was the technique, or a similar technique, that was developed by Nobel laureate Pierre Agostini. He developed something called the rabbit technique. He could show that he could not only produce attosecond pulses, but he could also measure the width. And they turn out to be 250 attoseconds. And this experiment was done in Paris, Saclay, in 2001. Almost at the same time, the other laureate, Ferenc Krauss, developed a streaking technique, which is a little bit different, but similar principle. And he produced so-called isolated attosecond pulses, 650 in pulse width. And this was done in Vienna in 2001. And these two platforms are the existing platforms in attosecond physics up to this day. Of course, the experiments have been improved much, but it's basically these two different techniques that are in use. And the choice, rabbit, which stands for reconstruction of attosecond beating by interference of two-photon transitions. But so depending on the application, you decide, do you want to use a pulse train with the rabbit technique, or do you want to use isolated pulses with the streaking technique? And what you can see here is that you have the attosecond pulses, overlap with infrared probe pulses, atom ionization, the electron coming out, and you get a signal which is a replica of an attosecond pulse. So by measuring this electronic signal, you can get an understanding of what is the pulse width. What can you do? Well, here is an example of how one can study photo emission delay. The question here arises. Let's take a neon atom. Let's expose it to an attosecond pulse. And the question is, if the electron is in the 2s, more tightly bound in the atom, or if it's more loosely bound, like a 2p electron, do they come out with at the same time? No, they don't. It was actually possible to figure out, by doing these experiments, that one electron goes faster out by 20 attoseconds. An incredibly short time that was actually possible to measure. And this was an experiment done in Lund. So let's go to applications, because I know that you will ask about that. With the attosecond physics and science, we have come to the point where we can have localization control of electrons in a molecule. This is a new field that can be called attochemistry, where you can locate electrons in a molecule and you can figure out what they are doing, jumping around. Ultrafast switching from insulator to conductor. This is a dielectric material, for example, silicon dioxide. You can switch with an attosecond pulse between a situation where this dielectric is not conducting, it's an insulator, but in 1 femtosecond, you increase the conductivity by 18 orders of magnitude. And of course, this is an important field because it gives you possibilities to develop very fast electronics based on these short pulses. And the final example, which is now being pursued by Ferenc Krauss now in Garching, is molecular fingerprinting applied to biological samples. So what is this? Well, you have a blood sample. You expose it to a very, very short infrared pulse. This infrared pulse will vibrationally excite the molecules in the blood sample. And there are literally thousands of molecules in this blood sample. And then they emit infrared, and you you detect this, and by analyzing what you detect, you can, and doing this with attosecond precision, you can draw conclusions whether there has been any change in the blood sample. So the idea here is not to analyze all the 1,000 molecules, but to find small, minute changes. And by doing this, there is the hope in the future that you will be able to capture whether a person have developed, for example, lung cancer in the body, so that you have a very sensitive method, and if you can diagnose cancer at a very early stage, treatment will be much more successful. So this was just a few examples, and I'm sure that you have a chance to ask the Nobel laureate afterwards. So I thank you now for my presentation, and we have them here again. Pierre Agostini, Ferenc Krauss, and Anne Lullier. 4 experimental methods that generate attosecond pulses of light for the study of electron dynamics in materials, in matter. Okay, thank you.
Thank you, Professor Larsson. Now we shall see if we have one of the laureates online. Professor Anne Lullier, are you with us on phone from Lund?
Hello, yes. Can you hear me?
I can hear you. Good day, Professor Lullier.
Hello.
Can you hear us?
Yes.
Yeah. Please accept our warmest congratulations for receiving the Nobel Prize in Physics 2023.
Thank you very much. It's just fantastic.
Yeah.
Thank you a lot.
You were in the middle of something when we reached you on phone an hour ago. Can you explain?
I was teaching. So, yes. So I picked the phone when I guess you ring the 3rd time or 4th time during the pause. And then the last half hour of my lecture was a bit difficult to do, but yes.
Yeah, it was fascinating. We had a lot of information to provide you with, Professor, but you were so keen to go back to your students, so we had to make a short call. I think it's fantastic to see how you combine world-leading research with being a very active and important teacher.
But, you know, teaching is very, very important. So for me, it's very important, and it's, yeah, it's a nice compliment, and yeah.
Yeah.
Sorry, I am not very good at speaking, but that's because I am very touched at the moment.
Yeah, that's understandable. I'm sitting here in the session hall at the Royal Swedish Academy of Sciences. Here we are casting live from the press conference. There are many journalists here, both from Sweden and from the international press. Are you ready to take some questions from them?
Yes, of course.
Okay. Who would like to start? Thomas von Heine.
Thomas von Heine, SVT. Grattis, Anne.
Tack så mycket.
Congratulations. We heard something about practical applications already. In your words, what's most important possibilities ahead from this technique?
In my work, I see 2 things. One is, which is very fundamental, and which is to really understand, look at electrons and look at their properties. But the second one is much more practical, and it's coming. It's this radiation that we produce is also useful for the semiconductor industry as a imaging tool. So this is also coming with practical application.
Yes, please.
Congratulations, Anne.
Thank you very much.
I'm from Forskning och Framsteg and PhD student at Department of Physics in Lund. So I look forward to congratulate you in person. I'm curious, what does this prize mean to you?
Hello, sorry, it was stopped.
Sorry.
Yes, please repeat the question.
Yes, of course I can hear you're very touched. And what does this prize mean to you?
It means a lot. It means really a lot. This is the most prestigious prize, and I am so happy to get this prize. It's incredible. And as you know, there are not so many women that get this prize, so it's very, very special.
Yes, of course. Thank you.
TV4.
Hi, I'm Anna
Hey.
on TV4. Yeah, I think you're the fifth woman, if I'm correct.
Closer.
I think you're the fifth woman, if I have calculated all right here. Congratulations. My question is that you could use this technique to locate electrons, but according to Heisenberg's uncertainty principle, you can't really say where an electron is. Of course, it can be somewhere in a cloud, but you can't really tell where it is in this cloud around the atom, or can you?
No, we cannot. We are certainly not violating Heisenberg principle. But, for example, you can see whether it's on one side of a molecule or on the other, but it's still very blurry. I mean, again, we are within quantum mechanics. So we are not. You should not have this image where we follow a point particle going around an atom. This is not what we are doing. But so we are within quantum mechanics, but we are getting new information about the electrons.
Okay, so what you can actually see is how a molecule, where the charge is, if the electron is in like.
This is the goal. Yes, this is the goal. I can tell you another. I think image is in this type of process that we are looking at. The electrons are much more like waves, like water waves, than particles. And what we try to measure with our technique is the position of the crest of the wave. So this is another maybe image you can have. And what we try to get information on is the dynamics of the electron. What is the time it takes for electron to move and, for example, to go away. That's our goal.
Thank you. It was a very good question. Please.
Associated Press here. Now, obviously, this is a prize that rewards fundamental research. People are interested in theoretical applications, of course. But could you maybe address the importance of this fundamental research and how important it is to see potentially public institutions being investing funds into this fundamental research when there is indeed lots of interest, maybe potentially too much interest in practical research? If you could maybe address that point.
Well, I think this is a typical example of research which is very fundamental. We have been working in this field during 30 years. Only now you begin to have application in sight. So basic research is really important and has to be funded by different institutions or agencies because it takes time. It takes time to arrive at a point where we start to see application for medicine, for semiconductor industry, for chemistry. So, but all the drive in this research has been extremely fundamental. Can we create short pulses? Are these pulses short? And then what can we do with it?
Yes. Please.
Yeah, I mean, this I mentioned already. There are applications coming up in the industry, in chemistry, in medicine. But yeah.
Yeah. We have one more question here.
From Nordic Chinese Times, and I wonder the potential of this attosecond technology in studying photosynthesis or how photopigments working.
The dream is to be. I mean, we are. This radiation is talking to the electrons, and when you have a chemical reaction, which is induced by absorption of light, like in photosynthesis. This is also always started by some electron transition. And then you have things that happens in the molecules, but the beginning is driven by some electronic transition. So the dream, if you want, the holy grail of this part of our research is to be able to control this initial time for a molecular reaction. And if you can do that, maybe you can control some reaction, and why not have some more insight into the process of photosynthesis. But this is in the future.
Okay, is there someone more who would like a final question from here?
Hej, Simon Campanello på Dagens Nyheter. So you have been studying this field since the 1980s. At what point did you realize what a breakthrough it was? Did you that land already from the experiments in the 80s, or when did you come to that conclusion?
I would say I was personally fascinated by this field from the start. And this is why I continued with it during many, many years. But I think there has been several steps, and one important step was by my two colleagues, Pierre Agostini and Ferran Cross, in 2001, where they really showed that we had very, very short light pulses experimentally. So this was an important step that really showed to the whole community that yes, we could. This could have fundamental applications, very interesting. But personally, I have been completely passionate by this field from the end of the 80s. And what is very interesting, it's a relatively slow field. It's difficult experiments. There is progress all the time, and we need lasers to produce this radiation. Lasers are progressing, so it's really a field that has been progress and is still progressing today, which makes it very interesting.
Thank you very much, Professor Hyllier. Once again, our warmest congratulations.
Thank you very much.
We look forward to meet you in Stockholm here in December for the Nobel Prize ceremony.
Yes.
So bye now, for now.
Bye.
Time is almost running out, but we may have time for one or two questions to the committee, if you would like to ask the members something. Yes, please.
I'm Shifichen Aksasong from Green Post. As a very non-scientific person, I feel lost, actually. So I ask you to use simple words to explain a little more why they won this prize.
Please.
Yeah, thank you.
Mats?
Yes, it's a good question, of course. You will have access to the popular science reports about this prize, but I think that in general you can say that in physics, when you manage to break through new frontiers, you will learn a lot of new things. And of course, it's always the first important step is to try to understand the processes, and can we then master them? And once you are in the situation where you both understand and you have the technology to master these techniques, then you can start thinking about the applications. And we are right now in that situation, right now. So, for example, 10 years ago, I think it was just too early to think about advanced applications. The researchers were still in the process of trying to figure out how everything worked and how to master it. Now, of course, there has been a development of laser technology in recent years, so that lasers that required many people to operate, now it's more, they are much more user-friendly, which means that many more research groups can enter these fields, because it's just not so technically difficult to operate the lasers anymore.
Mm. There's time for one final question from the journalists here, please.
Thank you. Excuse me. David Keaton again from the Associated Press. Have you managed to contact all of the winners, and how have they responded, if so? What was their reaction, if you managed to speak to them this morning?
Well, you heard the reaction of Professor Hyllier. She is thrilled, of course, by the message. We got hold of one of the other laureates, and he was equally enthusiastic, of course, about this. You will find out. I think time has run out. Thank you for your interest. We hope to see you again tomorrow when we will announce the Nobel Prize in Chemistry.